Hi everyone. So this is a video that introduces Kirchhoff's rules, which are the most powerful tool for analyzing circuits. The circuits we've seen so far, we've pretty much been able to analyze just by turning the capacitances, the various capacitors there, into some equivalent capacitance, then figuring out how that equivalent capacitor behaves, or turning the resistances that are in the circuit into some equivalent resistance, and then figuring out the dynamics of the system based on that. But there's a whole bunch of circuits, almost all of them in practice, that can't be reduced in this way. And we need slightly more powerful methods, more general methods to do that. So there's two Kirchhoff's rules, a junction rule and a loop rule. And they will be familiar once I say them, but I want to state them and show how we can use them. I put a circuit here to the left that we're going to analyze, and I'll talk about that as we go and use that as an example as I introduce the rules. So this will be kind of a problem-solving video in parallel to this discussion of conceptually what the rules are. So there's two rules. Here are our rules. There's a junction rule. So there's Kirchhoff's junction rule, which says that there's many ways to state this, but the way that I will state it here is that if you have a junction in your circuit, all current entering the junction must sum to all current exiting the junction. So what does that mean? I guess first let's define what a junction is. So if you look at the circuit we have here, a junction is anywhere where there's a split in the wire, where the current would have a choice. So for example, at this spot right here, if I call this point A, that's a junction because there's three wires leaving point A. I guess a way to state this more generally is if I drew a point, like if I picked another point here, say, point B, let's say, B is a junction of sorts. There's a change in direction of the wire, but there's really nothing interesting happening here because the current will just flow in a straight line around this curve. There's nowhere else for the current to go. At point B, I could say that all the current entering point B, entering that junction, has to be the same as all the current leaving the junction. But all that means in principle, in practice here, is that the current in the wire that point B is on has to be the same entering B as it is leaving B. It's slightly more interesting at point A, and let me define some other things here. So I'm going to define currents. Usually what we do in problems like this is we say, I don't know what the currents are here. And typically what you want to do in a problem like this is figure out what the current is everywhere in the circuit. So I don't know what those are, but I'm going to define variables for them so that we can work and solve for them. So the way that works is I'm going to define the current here to be I1. I'm going to define the current here to be I2. And I'm going to define the current here to be I3. I've called them that because I1 represents the current that's passing through resistor 1, I2 represents the current passing through resistor 2, and I3 represents the current passing through resistor 3. And one consequence of the junction rule is that I1, if I1 enters point B, and it exits point B too. So I1 is the same everywhere on this little partial loop. So I1 is the same everywhere there. I2 will be the same everywhere here. I3 will be the same everywhere here because there's nowhere else for the current to go. So any point I checked on any of those wires, the current entering would have to be the same as the current leaving. There's no way to reduce the current or increase it or anything like that. So now that I've defined currents, I can look at point A and analyze what's happening there. So at point A, I've defined the currents to have some direction. So there's two currents entering point A and one current leaving. The currents that are entering are I1 and I2. Those are entering A because I've drawn them with arrows that point towards A. And then I have I3 leaving. It's got an arrow away from point A, so it's leaving. So I1 plus I2 enter, I3 leaves. The junction rule says that I1 and I2 have to equal I3. That's how we would use it here. That's really useful. Another way of conceptualizing this and another way to state the junction rule is that charge is conserved in a circuit, and there'll be no places in the circuit where charge just builds up over time. So what would it mean if I1 and I2 were bigger than I3, for example? It would mean that there'd be this huge deposit of charge at point A. You just get like more and more charge building up at A because there'd be more charge per time entering A than leaving A. And in practice, we never observe that happening in a circuit exactly unless we've got, say, a capacitor, but we're not necessarily talking about those here. Okay, so that's junction rule, useful. I should also note that there's another place where there's 3 wires, this spot down here, right there. But you'll notice that that doesn't actually get us any more information. If we wrote down the junction rule, we would get the exact same equation as we did for point A. And so it doesn't add anything for us to do that. Okay, so next rule is the loop rule. So again, there's many ways to state this rule. The way that I'm going to state it is that the change in potential, or the delta V, the potential difference around any closed loop in the circuit is 0. All right, so what does that actually mean? Well, let me take my point B again. So let me look at point B. So here's point B. If I started at point B and I traveled around any closed loop and ended up back at point B, so if I say, like, if I was a charge and I moved around this circuit this way, along this path, along this path, along this path, back to point B, if I do that path, then the total potential difference that I move through is 0. So what that means is that the potential at B is something. If you start there and end there, your potential will be the same when you started as when you ended. So the potential difference along whatever path you traveled to get back to where you started has to be 0. That's all the loop rule is really saying. It turns out that this is a really powerful and important rule for us because we can write some things down that are true based on that rule. So let me draw a couple other points and I'll show you how to implement this rule. So these points are going to be B. So, excuse me, one point is going to be purple. So here's a purple point. Let's say that I take this point and I take a loop. So I take a loop and I'll call it loop 1. This is where loop 1 starts and ends. And loop 1 is, I'm going to start at this point and I'm going to go this way around the circuit. So I'm going to travel clockwise around the circuit all the way like this, like that. Even though I've drawn it sort of weird, it's not connected to the circuit, you can imagine a charge moving along the circuit this way, kind of like this, along the wires, passing through all the stuff that it has to pass through to do this, because we're constraining our charges to move in the circuit. But I'm taking a clockwise loop that starts and ends at that purple point right there. So what does the loop rule say? It says that if I have loop 1, so loop 1, if I add up all of the potential gains and drops along that path, I should get 0. So let's look at this. So what are the potential gains and drops along the path? Well, first, I move along a wire, and there's no potential gain or drop along the wire. Then I get to this battery. And the way I've drawn the battery is there's a low side to the battery on the right. This is a low side, and a high side to the battery on the left. That's a high side. So if I pass the battery going right to left here, I gain voltage equal to V2. So the first thing that happens on this loop is that I gain V2 voltage. Then as I continue to go on this loop, I go this way, it's just a wire, nothing happens. I get to the resistor. So now there's current flowing through the resistor this way. And if current flows through a resistor, then the voltage drops in the direction that the current is flowing. So there should be a higher voltage here. Then there is a lower voltage here. So higher voltage on the low side, higher voltage below the resistor here, and lower voltage above. So I'm losing voltage as I go across that resistor. And how much voltage am I losing? Well, that's Ohm's law. So Ohm's law tells us how much voltage difference there is across a resistor. So the current times the resistance gets us that voltage drop. So I lose minus IR. I1 R1 is the voltage drop across that resistor. And then I move along the wire until I get to this battery, but now I'm moving from the high side of the battery to the low side of the battery. So that's another voltage drop. So I lose V1 volts as I move across V1. And then I continue to move along the path until I get to R3. And similarly, I'm moving with the current. So I'm moving from a higher voltage here to a lower voltage here. And I lose the voltage of that battery as I move. So that's I3 times R3, using Ohm's laws again. And then I get back to where I started. So that means that the total voltage difference from beginning to end, adding up all these differences in voltage, has to be equal to 0. Okay, I can plug in numbers here too. I won't do that just yet. I can write down another loop if I want to too. And let me do that as well. So this first loop, you'll notice, has no information about that middle leg, this middle leg right here. And if I want ultimately to figure out what's going on everywhere in the circuit, I'm going to need a loop that tells me about that middle leg. So let me try to come up with that. So I'm going to pick a new spot. So here, let me pick a new spot right here. So this is loop 2, starts and ends there. And let me go, in this case, counterclockwise. I can pick my loops to go any way I want. All it does is flip the signs of everything in the loop that I'm tallying up. I'm going to pick this one to go counterclockwise, just to show you what that looks like. So here I've got a loop starting there, going this way, around this way, through this resistor, and then back to the start, counterclockwise. So let me do loop 2. So loop 2. So I start going counterclockwise, I get to this voltage. In loop 1, it was a negative change in potential across that battery because we were going from high to low, but here we're going from low to high. So we actually get a potential gain of V1 here. So we pass that battery, gain V1. Then we pass through this resistor. In the previous loop, that was a voltage drop, but here again, it's a voltage gain because the current is passing up through that resistor, which means that there's lower voltage here on top of the resistor and higher voltage here below the resistor. So I get a voltage gain as I pass the resistor here. So that's I1 R1 with a plus sign because I gain that. And then as I continue to go around the loop, I get now to this middle leg with the resistor. And now I'm moving with the current again. So there's higher voltage here below the resistor and lower voltage here above the resistor because I'm moving with the current. And there's a voltage drop across the resistor with the current. So that means that I lose the voltage drop across that resistor in this loop. So I2, R2, using Ohm's law again, and then I'm back to where I started. So the total adding up and subtracting all of the voltages there, the changes in voltage have to be 0. Those are 2 loops. So just to step back again, these rules are great, but the reason why we're using them is because we're trying to figure out what the current is everywhere in the circuit. What we know are these quantities on the left. We know the voltages of the batteries. We know the resistances of the resistors, but we don't know the currents. And what we're trying to do is find the currents. You'll notice that there are 3 different currents in this problem. There's 3 pieces of wire essentially here, and each of them will carry a unique current, or I guess not. I guess they don't have to be unique, but 3 different currents. None of them will be the same. So we're going to need 3 equations to solve for 3 unknowns. And you'll notice that I have 1 equation from my junction rule, and I have 2 equations from these loop rules. I could draw more loops, but just like with the additional junction that we could have considered before, we're not going to get any more new information from that loop. If I took a loop that was, say, the right loop here, so if I started at the purple point and then just did this loop, for example, I'm not really learning anything new because that's equivalent to just adding up the 2 loops that I have already. And you can see that and try that for yourself if you want. I don't really learn anything new by doing that. But I don't need to learn anything new because I can already solve for what I want using these 3 equations. 3 equations, 3 unknowns, in principle it's solvable. So now what I'm going to do with the rest of this video is show you how to approach solving that. If you feel really comfortable solving systems of equations, great. Hopefully this will make sense. If not, then consider this as a way forward in a problem like this when you don't really know what to do. So let me fill in some values. In loop 1, I can fill in values here. So V2 is 6, R1 is 2, so this is minus 2I1. V1 is 3, minus 3, and R3 is 5, so this is 5, R3 equals 0. So that's an equation that has I1 and I3 in it, and those are the only 2 unknowns there. In loop 2, I've got V1 is 3 plus I1 R1, R1 is 2, so that's 2I1, minus I2 R2, R2 is 4, so minus 4 I2 equals 0. All right, so let me scroll down for some more space. So there's our general goal here. Solve the system of equations for the current values for I values. And then we'll basically know everything there is to know about this circuit. Oh, one thing I guess I should mention before we move on is you might be wondering how I decided on the currents. So I1 I have in going this way, sort of clockwise around the loop this way. I2 I have going up, I3 I have going this way. And how did I know to draw them that way? The answer is that I just picked directions arbitrarily. And it does not matter which way I chose the currents to be. If I chose the directions correctly, I guess, in the direction of the actual current flow, I'll get positive values for the currents. If I chose the directions incorrectly, that is the currents as I drew them point opposite of the actual current flow, then I'll just get negative values for the currents. And so it'll work itself out. But so what that means is if we get to the end of this and we have some positive values for current and some negative values for current, what that means is that I chose the correct direction for the current if I get a positive value at the end, numerical value, and I chose the opposite direction for the actual current if I get a negative value out at the end. And so we can keep that in mind when we interpret the values at the end. But you can always arbitrarily set the directions of the current to be whatever you want, but then you have to just be careful about the signs of the voltage gains and drops that you have in your loops. And the junction rules will look different because which currents are entering and exiting the junctions will be different too. Okay, so let's try to solve this. So our goal is to solve the system of equations for I values. We've got 3 equations. I'm going to label them all. So equation 1 is our junction rule. That's just I1 plus I2 equals I3. Okay, we've got another, and now we got a loop rule. Our loop rule is 3 minus 2I1 minus 5I3 equals 0. And 3 is 3 plus 2I1 minus 4I2 equals 0. Okay, let me just double check to make sure that that is right. Okay, looks good. All right, so how do we do this? This is just a complicated algebra problem essentially at this point. And what we want to do is we want to systematically eliminate variables until we just have an equation that only has one variable in it. Right now, we can't just solve this directly because every equation has more than one unknown. And the goal of this is to reduce these equations until you get equations that can be represented with just one unknown. So the way we do that is, well, here's a method to do it. I think there's lots of ways to proceed from here. But let's first use equation 3 to, we're going to eliminate I1 this way by writing I1 in terms of I2. So we're going to write, we're going to rearrange this equation and say I1, if we move I2 to the other side, subtract, so that would be 4I2 minus 3 over 2 is I1. And that's just algebraic manipulation of equation 3 right there. So that is I1 is equal to 2I2 minus 3/2. Okay, so now we have eliminated I1 as a variable in favor of I2. So let's see how that works. So now I'm going to plug this equation, plug this expression into equations 1 and 2. So now equation 1 becomes, we can replace I1 in equation 1. So I1 becomes 2I2 minus 3/2 plus I2 equals I3. Okay, so if I simplify that a little bit, I can add that the I2 terms together, and I get 3I2 minus 3/2 equals I3. Okay, so that's one equation. So now we have eliminated I1 from equation 1. So now there's just 2 unknowns. And now we're going to do the same thing for equation 2. So in equation 2, we now have 3 minus 2, and then we substitute for I1. So 2I2 minus 3/2 minus 5I3 equals 0. So now if we look at this, we've got 3 minus 2 times minus 3/2, so that gets us 6. And then we've got minus 4I2, and then I'll move the I3 to the other side, is 5, or excuse me, let me not do this, minus 5I3 equals 0. Okay, so now if you look at our modified equations 1 and 2, those are now 2 equations with 2 unknowns. So we've made it a simpler system of equations. And now what we're going to do is we're going to substitute equation 1 into equation 2. because equation 1 is now an expression for I3 in terms of I2, which will enable us to just put that equation 2 in terms of I2 alone. So let's see how that works. So now I'm going to do 6 minus 4I2 minus 5 times I3, and substituting for I3, 3I2 minus 3 halves. That's equal to 0. So now let's expand this in group terms. So we have 6 minus 5 times minus 3 halves. So 6 plus 15 halves. 15 halves is 7.5. So 6 plus 7.5 is 13.5. And then we have minus 4I2 minus 5 times 3I2. So minus 4 minus 15 is minus 19. I2 equals 0. And now, scrolling down for a little bit more space, this means that I2 equals 13.5 over 19, which is approximately equal to 0.711 amps. So the units of everything here are amps, because we've been using SI units, volts and ohms. Okay. All right. So next, now we have I2, and now it's just a process of working backwards to get I3 and then I1. So we have I2 as a numerical value. Oops. Try to draw that better. Okay. So if I2 is 0.711 amps, or 13.5 over 19, then we can use this expression we had above. So we have this expression, which tells us I3 in terms of I2. So then I3 should be equal to 3 times I2, which is 13.5 over 19, minus 3 halves. And if you do that, I get 0.632 amps. So that's I3. So now we know I2 and I3. There's lots of ways to get I1 at this point. I guess I'll use this equation here. I1 equals 2I2 minus 3 halves. So if we want I1, we do 2 times I2, 13.5 over 19, minus 3 halves. And if you do that, you get minus 0.079 amps approximately. Okay, so now that's our solution to the system of equations. 3 equations, reduce the equations down until we could solve for one of the variables and then plug back in for the other variables. And that's the way that all of these problems go. Sometimes the equations to solve are more complicated than the ones here, but if you can figure out how to do these substitutions, you can always in principle solve them as long as you have as many equations as you have unknowns. All right, so looking at these numbers, is there any intuition we can get from the numbers? So let me go back up to the top and label some of these currents. So I1 now is minus 0.079 amps. I2 is 0.711 amps, and I3 equals 0.632 amps. Okay, so do these values make sense looking at them? So if you think about the physics of what's happening here, we've got V1 and V2, and they're kind of pushing against each other in a way. V2 is bigger than V1, but what this is showing is that actually I1 is flowing in the opposite direction of what I labeled it. So there's current flowing counterclockwise in that loop, what was loop 2 before. So there's current kind of flowing counterclockwise in this loop. That's what the minus sign means. But there's not very much of that current. Most of the current is flowing in this loop here, like that. And you get big current flowing here. And then when you get to this point, the current splits. Some of it goes this way, 0.632 of it goes that way, and 0.079 of it goes that way. So that's what the result means physically. And now we know everything there is to know about this circuit. So I hope that was helpful, gave you a sense for how to analyze circuits like this using Kirchhoff's rules. And I will talk to you soon. Bye.